In this example of a statically indeterminate system, we've got two fixed ends for this cylindrical rod, two very large forces, a 70,000 concentrically applied load, 70,000 pounds or 70 kips, here at 8 foot from the left end, and a 30 kip load going directed to the right, 4 foot from the other end. Right, so our locations here are A, B, C, and D going from right to left, not left to right. There's a lot of different ways that one could approach this problem, but a common one is to use superposition, especially if one's going to do this by sort of a hand calculation technique. So, for instance, what we can do is we could remove this support at the right as our first step. Let's remove our reaction A. And when we do this, we're going to impose the actual loads. Some people will now call this the primary system with the primary or actual loads applied to it. So there's our 30 kip, there's a 70 kip. And find out how much displacement has happened at point A. Now we've done this previously, and we find out that this member actually shortens or goes to the left at 0.0327 inches. Now keep in mind that in our real system here, that our reference here is right where A is originally. We'll take to the right positive, and we know that in that system there's not supposed to be any displacement. That's the fixed end nature of it. So when we relaxed or removed our redundant reaction and then calculate what our delta A is, we find out it's going to the left, or that in that system delta A equals minus 0.0327 inches. Now, because that's happening in a system where there is an R sub A, sometimes people put that next other subscript of a 0 there to indicate that there's no reaction there. But that, of course, doesn't conform to the original system. So what we'll do is we'll come back again with the primary system, meaning no redundant reaction in there. And then what we'll do is impose the unknown value of the redundant reaction to pull it back into place. And that, in this situation, of course, we'll elongate the member. That'll be your delta A for your redundant reaction. In more formal structural analysis models, we have a very specific subscript designation. This is a little bit sort of making it up as we go. And you can tell what it's going to have to be here. But formally what you would do is you would write your compatibility equation here that would say that in this superposition of these models, that delta A of the whole thing has to be equal to the sum of what happens in these two systems, delta A in 0 plus delta A when we reapply the redundant reaction. It's supposed to end up with 0 because that's what we have in the final system. We had minus 0.0327 inches in the first one, and then plus our unknown delta AR, and of course that's just going to tell us that delta AR is equal to A plus 0.327 inches. And now that's not helpful unless we have a model for how to calculate that, but in this nice simple case here, delta AR is going to be equal to the sum of the delta equal PL over AE of each segment, or NL over AE. Now in this case we have a system that has all the same force, right? And the A and the E will be constant all the way along the length. So we don't really have to break this up into multiple segments. We can do this all at once. We have R sub A, the length is 18 feet. Let's get that into inches right away. Divide that by our area, which has a 0.75 inch radius, square it, times pi, times 29,000 KSI, set that equal to what we know that value needs to be, 0.0327 inches, and solve for R, and we find out that our reaction at A then is going to be 7.76 kips, which is all we need to be able to do the rest of the problem, which asked us to find the resulting axial stresses in this statically indeterminate system. So if we come back up to a free body diagram of our rod, then you've got then a system that has 70 kips applied at C, 30 kips applied at B. We just found out that R sub A was 7.76, and if you do the resulting then equilibrium, then the reaction to the left actually has to be acting to the right. We got 70 going to the left, we only have 37.76 going to the right, so this reaction has to be acting to the right also. Not sure what I just said, but at the left side it's going to put this into compression, 32.24 kips, so that all of this will sum to be 0. If we were to plot the axial force diagram, kind of like the shear moment diagram, but just for axial forces, then N would start off, of course, at 0, immediately drop into compression or negative at minus 32.2 and change. It would hop up by 70 to 37.8 and change. It's really 7.6, and then it's flat over to where the 30 kip load is applied, and then that would drop down to 37.8 minus the 30. Really, again, it's 0.76, and you'd end up with 7.8 kips there. Right? We'd have tension in the right segment, tension in the middle segment, compression in the left segment, from which then you can calculate the axial stress in each segment. Sigma is going to be Ni over Ai. Of course, A is the same in each every one. You'll find out from in the CD segment that that's going to be 18.2 KSI in compression. Sigma in the middle segment will be the largest absolute value that we have, 21.4 KSI in tension, and then in that last one where we have 7.8 kips divided by the area, then that is a B segment, and that is going to be 4.39 KSI also in tension. And remember, area equals 0.75 squared times pi, and that will be in inches squared.